Click the bell icon to get latest videos from Ekeeda.
Hello friends, I welcome you all to this video. Here we are with chapter 2 of microwave engineering, a family of microwave linear beam tubes we have dealt with. So in this family we have gone through the understanding of two cavity klystron, multi-cavity klystron, both working as amplifiers. Multi-cavity klystron has achieved certain improved gain as well as improved efficiency. Reflex klystron as oscillator, and then the helix type of traveling wave tube that we have considered. So all these devices have worked onto the principle of velocity modulation, and after that we have gone through the understanding in the previous video for the coupled cavity traveling wave tubes for the purpose of achieving higher power. So for high power applications, these coupled cavity TWTs are used. Let us see the microwave characteristics. So here we start with our topic, microwave characteristics in coupled cavity TWTs. As we have seen in the previous videos that as we switch from a helix type TWT to the coupled cavity type of TWTs. So in the helix type there it was the use of slow wave structure. Slow wave structure is meant for adjusting the velocities of the signal that is propagating over that helix and the velocity of the electron beam. So if the electron beam velocity we denote by small v0 and the velocity of the signal onto the helix, the phase velocity v suffix ph, when they were approximated to each other, we have more and more interaction between these two energies and we finally achieve the amplification of the microwave signal. For higher power handling capacities, we have used here the coupled cavities. For coupled cavities, two types of circuitries we have seen in the previous video. Now, when it is the time to talk about the power handling with respect to these devices, there are two types of powers we must say. The first power is the average power and another power is the RF power. So let us take the second type of circuitry we have seen into the last video and discuss these two powers. So here we have a graph that plots frequency of operation in terms of gigahertz versus the RF power as output one in terms of kilowatts. So here we have the frequency ranging from 1 gigahertz up to 100 gigahertz. We have approximately plotted the values of the output power for 2 gigahertz up to 20 gigahertz. So if you see here, this is the portion representing the peak power with respect to the device. The device here, the circuitry that has been taken as PPM, that has the permanent magnets we have shown that are focused for the coupled cavity tubes here. Now here for the peak power, the voltage that ranges from 25 kilovolts up to 65 kilovolts here. So the corresponding output power can be calculated from this particular graph. Now on the other hand, we have the average power. The average power is having the voltage for V is equal to 25 kilovolts up to V is equal to 65 kilovolts, the same range as we have gone for the peak power here. So for average power, the consideration is with respect to the thermal characteristics of the circuitry under consideration, whereas for the peak power, the power handling capacity is somewhat different. So for the peak power, if you consider the parameter to be the voltage here, the voltage with respect to the electron beam focused between the two electrodes, the beam current can also be given. The beam current can be denoted here I suffix beam, and it is in terms of capital K into the voltage denoted by V suffix 0 that has a power 3.5 here, so 3 by 2. So let us say this is equation number 1 to calculate the beam current, where K is with respect to the electron gun that has been used at the cathode terminal. So this is actually the electron gun perviance. And for the coupled cavity traveling wave tube, the K value, the electron gun perviance value, ranges between 1 to 2 into 10 raised to power minus 6. So once for the device the K value is selected, further we can determine the beam current into that particular device. Now if you know the beam current, then we can have multiplication with respect to the voltage and finally find the beam power here. Therefore, for the beam power, we can have the relation given by capital P suffix beam is equal to capital K, again representing the electron gun perviance, V0 that is having the power 5 by 2. So K into V0 to the power 3 by 2 is already absorbed in this equation and it is further multiplied with respect to the V0 so that we have a product of beam current and the beam voltage so that the beam power can be determined. Let us say this is equation number 2. So I outline the important equation P beam here. So as in the previous video we have gone through the two types of circuitries used to make TWTs to be the coupled cavity TWTs. So here it was a plot of frequency and the RF power output in terms of kilowatts for the ppm focus coupled cavity tubes, that is of second type. So if we go for the first type, we have another plot here. So here for the first type of circuitry we can name here solenoid focus coupled cavity tubes. So again here we have a plot of frequency values onto the horizontal axis ranging from 1 gigahertz up to 100 gigahertz. So we have a plot obtained for the corresponding values of the RF output voltage in terms of kilowatts for 2 gigahertz up to here we have approximately up to 50 gigahertz. So here the beam voltage capital V here denoted that will be holding the value 20 kilovolts here. So as we have a device coupled cavity traveling wave tubes, the coupled cavities are been used here for handling higher amount of power. But as we associated with separate cavities here, there may be a chance of fluctuations in terms of gain. So to have reduction into the gain fluctuations, every cavity is supposed to be matched with a load here, or it is terminated with a matched load here. So overall we find that for the stability with respect to the frequency and the gain can be achieved greater than 60 decibels. The overall bandwidth can be used at these particular values to be of 30% here. So as in the device we have the interaction between the two energies, one energy in the form of electron beam focus between the two electrodes and another energy that is microwave itself. So the interaction efficiency in between these two energies we find for this device from 10% to 40%, and the overall device efficiency can be given in terms of 20% to 55%. So by the next lecture we shall be addressing the concluding topic in this particular chapter, that is high power and control graded TWTs here. I hope you are definitely getting good knowledge of microwave engineering. For more information like this, you can subscribe to Ekeeda channel. Thank you.